Hello, my name is Yi-Jie. I'm an engineer from Taiwan Semiconductor Research Institute. I'm really glad to have this opportunity to attend this conference and share my research with you. A portable power-efficient PM2.5 sensor system. First, I will give a brief introduction to talk about why we're doing this research. Then I'll explain the system development including the hardware architecture, verification experiment, and sensor calibration. Then followed by some experiment results, and at last is the conclusion. While environmental problem has always been an important issue, including global warming, climate change, deforestation, and all kinds of pollution. And one of the pollution that affect us most of the time is the air pollution, since we inhale about 10,000 liters of air every day. Air pollution comes from both natural sources and human activity, such as nature dust, industry and energy exhaust, and traffic waste. Poor air quality can cause damage to our health, especially when the toxic substance adhere to the particular particle and enter our body as we breathe. But how far can those particles go in our body, and what kind of damage would it cause? Particulate matter can be classified based on the size. For particular diameter less than 10 micrometer is called PM10. It can enter our nasal cavity and reach our throat, causing respiratory ailment and allergy. PM2.5 are particle diameter less than 2.5 micrometer. It can go further to our lower respiratory system and past the bronchus, increasing risk of lung cancer. The diameter less than 1 micrometer can go deep into lung passageway and enter the bloodstream, which can cause cardiovascular disease. With all those terrible diseases, of course we will wish to know the particular matter concentration around us, so we can do something to prevent to inhale it. So research and commercial product about particulate matter monitor has become popular and common. But how do we acquire PM information if we don't have those expensive equipment? Well, there are several ways to know the PM concentration. We can go to the Environmental Protection Agency website to look up the PM concentration in the past 1 hour. Or there are lots of IoT PM monitor systems combined with app. However, those solutions are usually not personalized, which means the PM concentration you are looking might come from a station far away from you. Therefore, there are many commercial products for home use on the market right now, but those products are usually designed to place at home, need power cable or battery to work, so it will be difficult to carry around if we want to know the outdoor PM reading. So we came up with an idea to design a portable, easy-to-use, and battery-free PM2.5 sensor system. We referenced the concept of a portable storage device designed for smartphone, with the interface of micro USB and Apple Lightning. It powered by the host device and communicate with the host running Android or iOS system. Combine this feature with a PM2.5 sensor. We proposed a portable PM2.5 sensor system called PAS PM2.5, where PAS means plug and sense. User can directly plug the PAS into their smartphone and start sensing the environmental information. The hardware architecture of the proposed plug and sense system include a host interface unit, a control unit, and a sensor unit. The host interface unit is a connector, support micro USB, Type-C, and Apple Lightning interface. The control unit can be a microprocessor or a FPGA, which is responsible for data processing and communication. The sensor unit can be different kinds of sensors. In this case, we apply the PM2.5 sensor. The concept seems very easy, but the PM2.5 sensor will usually contain a fan to draw the air into the sensor and consume more power than the mobile phone can provide. To solve this problem, we designed an energy storage hardware to provide enough power for the system. And this is the hardware architecture of the PAS PM2.5 with the energy storage function. The host interface included a Lightning connector to acquire the power from the iOS device and transmit data. A microprocessor is responsible for reading sensor data, control the voltage booster, and monitor the supercapacitor. The supercapacitor can temporarily store the power, and the voltage booster can provide correct voltage that the sensor needs. For iOS system, to ensure the device can be identified and work properly, a coprocessor is required for legitimacy reasons. And now I'm going to explain how does it work more closely. As the PAS PM2.5 connect to the iOS device, the device will proceed the authentication by using the coprocessor with certain protocol. As the authentication succeeds, the iOS device will start to provide power to the system and communicate with the MCU. In the beginning, the voltage booster is off and the supercapacitor is charged through the low switch, which is designed to limit the charging current. Meanwhile, the MCU monitors the voltage of the supercapacitor. As the voltage has reached the threshold, the voltage booster will be enabled and activate the PM2.5 sensor. Then the MCU will start to acquire the sensor data and continues to monitor the voltage of the supercapacitor. As the capacitor voltage has dropped to critical low, the voltage booster and PM2.5 sensor will be disabled. Then the capacitor can continue to recharge and start another operation cycle. As we mentioned earlier, the PM2.5 sensor will keep turning on and off pretty much every 30 seconds. To verify the continuous switching operation mode and confirm the sensor reading accuracy, we perform a comparison test with two identical PM2.5 sensors placed side by side on the window sill and with the window wide open. One remains active and another one switches every 30 seconds. The sensor data are acquired every 60 seconds, and the experiment was run for 5 consecutive days. The result is shown in the figure on the right. The vertical X indicates the sensor reading of normal active operation mode, and the horizontal X represents the sensor reading of switching on-off operation mode. The result shows that they are well correlated, with R-squared around 0.98. So we can verify the switching mode will not affect the PM2.5 reading. With the experiment result and the hardware design we mentioned earlier, this is the printed circuit board of the proposed PAS PM2.5 sensor system. The PM2.5 sensor, the supercapacitor and lightning connector are placed on the top side of the circuit board, while the MCU chip, coprocessor, and other components are placed on the downside. The overall size of the circuit board is 51 mm wide and 43 mm long. And this is the usage scenario. After the PAS PM2.5 is plugged into the iOS smartphone, the app will be launched automatically, and the user can observe the real-time PM2.5 concentration in the environment on the app. As we can see from the last slide, to make the system small and affordable, we use a low-cost laser scattering PM sensor. However, most of the low-cost optical PM sensors are easily affected by environmental factors, such as temperature and humidity. So we apply those two factors into a calibration equation as shown in equation 1. With the temperature and humidity variable goes with the original PM reading, we can then get a calibrate PM2.5 data. To build up the linear regression model for the calibration equation, we took a 45 days long field experiment, cooperated with the local Environmental Protection Bureau. We placed the optical PM2.5 sensor close to the environmental monitor station and collect data at the same time. The station is equipped with meteorological sensor and continuous particular monitor. With those reference data, we can then build a linear regression model for the low-cost PM sensor. At last, to estimate the actual power saving, we compared two sensor systems, one with the proposed energy storage hardware and switching operation method, while another one is without them. We used the accessory test system to monitor the actual voltage and current that the PAS PM2.5 consumed from the mobile phone. And the comparison results are shown in the figure here. The average power consumption of the non-energy storage architecture is about 374 milliwatt, and another one with proposed energy storage architecture is about 254 milliwatt, which means that the PAS PM2.5 adapt with the proposed energy storage architecture can save up to 32% power consumption. Finally, the conclusion. In this paper, we proposed a portable power-efficient PM2.5 sensor system named PAS PM2.5, which can support the micro-USB and Lightning connector, and it adapts an energy storage architecture and switching operation mechanism, which can save 32% of the power consumption. We also apply a linear regression model to calibrate the sensor reading to make it more accurate. In the future, hope that we can provide cloud server to collect those data for research purpose. And thank you all for your attention today.